Okay, I think we have to start. I'm really sorry to mess up with the start time on the event page. So please do check out the recording if you find this is helpful to you. So my name is Nancy. I'm a software engineer in Meta. I focus on ads ranking area. And today I will talk about the basics of constructing a machine learning system that can rank ads and provide personalized recommendations. I will guide you through the entire pyramid, starting from raw data, what it is made of, and how it is being processed. Then we will proceed on to the process of ranking with all of its stages and typical models involved. Finally, we will see how to tackle typical problems that arise when our entire recommendation system is still in the early stage and some of its components or incoming data is totally new. This talk will take around 30 minutes. And so let's get started. We should start at the very base with an explanation of the features that is commonly used in the ads ranking systems. These features constitute the foundation of our data. They are basically the things we should know to make further aggregations, comparisons, and ultimately predictions. These features form two major blocks, namely user set features and ad set features. For user set features, there are usually three different categories of user set features. The first one is user description features, which enable us to know who the user is and what his or her connection networks are. This kind of features can be, for example, the age of the user, the gender of the user, country, the list of followings and followers of the user, etc. Another category is user behavior features, which tell us what the user did. For example, the user's past clicks, add to carts, purchases, or user past ratings for different items, or just a list of ad IDs that led the user to a purchase, or just users' average click-through rates in the last 90 days, etc. The last category is context features, which give us an insight into the user's environment, ongoing or expected events, such as user local time, user location, what season the user has at the moment, whether it is a public holiday at that location, etc. For the ad set features, usually there are two different types of ad set features. The first comes content features, which describes the essence, type, and contents of the ad, such as the ad category, the average price of products offered in the ad description, brand name, ad pictures, etc. As for the historical interaction features, which are also very important ad side features, they can describe that ads user perception. For example, the ad's average click-through rate or conversion rate, the number of likes, comments, and shares an ad has, etc. Usually, several pre-processing techniques are used on top of the raw features before feeding the data into the machine learning models. These techniques enable splitting data into segments, normalize it, or emphasize data parts that stand out. So the first technique is about normalization. This method will normalize the raw dense features into a range between 0 to 1, or a standard Gaussian distribution with 0 as mean and 1 as standard deviation. And the second technique is bucketization. This technique can discretize dense features into sparse features based on percentiles, for example. Let's see, we have a user age feature with possible values ranging from 0 to 100. And let's assume quartiles for user age are 25, 50, 75, and 100. Now, if we have a user aged 40, instead of having a dense feature value 40, this user will have a sparse feature that is a vector 0100 to describe the user's age. The last technique is nonlinearization. Nonlinearization operations can be applied on top of dense features so that more nonlinearity is introduced to the model and model capacity is further increased. Commonly used nonlinear transformations are, for example, square operation, uh, log operation, etc. For model training, data labeling is required. Every training data point is a feature vector and label pair, where the feature vector is a list of features we mentioned earlier, and the label is a binary value indicating whether the user has interacted with the item or not. This could mean that the user has clicked an ad or made a purchase via the ad or performed any other action we want the model to learn on. Since it is a binary classification, cross entropy is then used to measure the gap between model predictions and the ground truth labels. Next comes the stages of the ranking system. So, what are the different stages in the ranking system? In the industrial setup for recommending system designs, there are usually two different stages involved for a recommendation request, which are the retrieval stage and ranking stage. However, a third or a fourth stage can also be added depending on data volumes and the accuracy required. Speed is the reason why this multi-stages architecture is widely adopted instead of using a single giant model to rank everything. This design results in a balance between speed and accuracy. Let's have a look at the retrieval stage first. In the retrieval stage, the system quickly returns a pool of items that the user could be interested uh, in from a massive amount of candidates with the help of user side and item side features. Usually, simpler models are used in the retrieval stage for the sake of speed. Recall and AUC, it's usually more important in the retrieval stage because we want items of users' interest to be passed to the next stage as many as possible. The exact conversion rate for each item is not that important at the retrieval stage. Accuracy is something we would like the system to address further on at the ranking stage. Once the items returned by the retrieval stage are passed to the ranking stage, the model can leverage more complicated features, like user item interaction features or sparse features, for example, and also use more complex machine learning models to do the most accurate personalized recommendation that the system can afford. Thus, the retrieval stage emphasizes more on computing speed, while the ranking stage focuses more on the accuracy. Then how about the ranking stage? Let's talk a little bit more on this. The retrieval stage should quickly return a list of items that are potentially interesting to the user after selecting them from a massive pool. However, the list of items returned by the retrieval stage can still be too big to be processed by the ranking stage within a certain time frame. This is not necessarily true for every case because it all depends on the latency tolerance and the computing power the system can afford. But should this problem arise, a pre-ranking stage can be added between the retrieval stage and the ranking stage. This intermediate stage would employ a simpler model than the ranking stage, along with some user features and ad features, in order to perform a rough ranking of the results returned by the retrieval stage. We can consider this pre-ranking stage a compromise between speed and accuracy compared to retrieval and ranking. As a result, the number of items passed to the ranking stage can be further decreased while still keeping the recommendation accuracy. Most of the time, even though we carefully prepare, let's see, the top 500 recommended items, the user cannot consume all of them. We do not expect the user to keep scrolling down for new contents for a long time until all 500 items are consumed. Usually, the user would only check the top 10 results, making the remaining results a waste. Then comes the ranking stage, where we can use whatever features we have and the most expensive model we can employ, aiming at the most accurate personalized ranking result the system can deliver. The results of the ranking stage can be then passed to the stage called re-ranking stage, which is highly dependent on the business needs. Different strategies can be applied based on the requirement, such as deduplication, exploration, or variety. Now let's dive into the models that are commonly used at different ranking stages. So for the retrieval stage nowadays commonly employs the two-tower model, which is shown in the picture here. The idea is quite simple. The architecture consists of two fully separated towers, one for the user and one for the item, which is also at, as shown in the figure. Through deep neural networks, the model is able to learn high-level abstract representation for both a user and the item with past user-item interactions. The output is the similarity between user embedding and add item embedding, which represents how interested the user is in the given item. To further accelerate the online service, user embedding and item embedding can be pre-computed and stored offline. Thus, we only need to compute the similarity between user and the item embedding during online service. Regarding how similarity is measured, cosine similarity shown here and Euclidean similarity shown here are two most common ways to define similarity between two embeddings. So what is the exact difference between these two and how do we choose between them? Theoretically, cosine embedding, cosine similarity lies within the range -1 to 1, where the higher the number is, the more similar two inputs are. When cosine similarity is equal to 1, the angle between inputs is 0 degree. When the cosine similarity equals to -1, the angle between inputs is 180 degrees, meaning that two vectors have exactly opposite directions. Meanwhile, the Euclidean similarity has an output range of -infinity to +infinity. The closer the output is to 0, the more similar the inputs are. The biggest difference between these two similarities is that cosine similarity is insensitive to the absolute distance in space. Only directional difference matters. So what does this mean? Let us use this example as an illustration. Let us assume we have user A who rates two movies at 4.4 and user B who rates two movies as 5.5. If we compute cosine similarity and Euclidean similarity separately for these two users, it's obvious that cosine similarity equals to 1, which means that there's no difference between these two users. However, the Euclidean similarity equals to 1.4, which means that user A and user B are actually still very different. Thus, Euclidean similarity is more strict than cosine similarity. For a complete match, Euclidean similarity requires users to have the same taste of movies and also the same level of liking to every single movie. But what if different users have different rating scales? For instance, user A rates two movies at 3.3 and user B rates them at 4.4. User A has a quite strict rating scale. This user's top score is just 3, while user B has a very loose scale granting 5s to more than 80% of the recommended movies. Intuition suggests that user A likes these two movies, while user B really does not. However, cosine similarity cannot reflect this. To calibrate cosine similarity, we can introduce Pearson correlation coefficient and use the user's average rating to calibrate every vote given by that user. So in the example from this slide, let us assume user A's average score is 2 and user B's average score is 5. To introduce calibration, we subtract the user's average score computed from the past behavior from each vote. And then after the calibration is applied, user A's vote is 1, 1, and user B's vote is -1, -1. Now the cosine similarity between these two users is -1, indicating that they are indeed very different. There's also another way to employ Pearson correlation coefficient. Instead of using calibration on the user side, we could use it on the item side. Let us assume user A provides a rating of 3.3 and user B a rating of 4.4. We have, let's say, 1,000 users who rated these two movies, and the average score for both movies is 3.5. Now, if we subtract this average score from the rating granted by our users, user A's rating becomes -0.5 and -0.5, while user B's turns into 0.5 and 0.5. Subsequently, their similarity becomes -1, indicating that user A and user B are actually very different users. For the commonly used models in ranking stage, one of them is DeepFM, a factorization machine-based neural network that balances both memorization, which is through the FM layer here, and generalization, which is through the multi-layers neural network. The FM layer just takes in raw features that could enforce the model to memorize a certain pattern in the training data. The other big advantage brought by FM is that it can support automated second-order feature cross, which improves the model expressivity. Deep neural networks conduct high-order feature cross and extract high-level abstract information. FMs and deep neural networks results are later combined through the logistic regression. So the output is based on both of them, enriching the model with memorization and generalization. At the ranking stage, we care most about the recommendation accuracy. So we can leverage as many features as we have and employ as complicated model architecture as the system can afford. So it is very common to add more blocks on top of the basic DeepFM framework to further enhance the model capacity. For example, we can add ResNet layers before the output logistic regression layer. We can also add an attention layer on top of the FM layer so that the model would focus on different information for different user ad pairs. For example, for some ads, if they have a clear target user age or gender, then features related to this information will have higher weights compared to other features. Finally, we need to know how to tackle cold starts. Cold start is a common problem with recommendation systems. Any such system takes some time to warm up before achieving a good performance level. A problem of giving recommendations before we have sufficient valuable data. It's known as the cold start problem. Cold start problem can be divided into three different cases based on what kind of data is missing: user cold start, ad cold start, and system cold start. So the first one, let's talk about the user cold start. As a new user is registered, it is hard to provide personalized recommendations without knowing this user's historical behavior. However, we could give a recommendation based on some rules. For example, under the user cold start scenario, the most popular items or top trending items or top rated items can be used as a default recommendation list. Actually, most of the music and video apps are using this kind of rules to tackle the user cold start problem. To move one step further, we can build up a simple recommendation model relying upon the information provided by the user at the registration stage. For example, if the user gave the age, gender, country, or IP address, some feature like this, we can use these simple features to build up an easy recommendation model and give a simple recommendation list. Then comes the ad cold start problem. When a new ad is created, there are no previous impressions coming from this ad, uh, as no user had any interaction with this before. How can the system target users for this ad? In this case, we can intentionally introduce more ad content features into the system. For example, the ad categories. For instance, if the ad is selling clothes or keyboards, and also ad tags, ad descriptions, etc., some features like this, which describe what is the content of the ad itself. To address the ad code start issue better, we can further introduce a dynamic attention weight mechanism for all the features. In other words, different weights are assigned to different user ad pairs. For example, let's say we now have a request from a user and there are two ads in the pool. We need to evaluate click-through rate for user ad 1 and user ad 2. We know that ad 1 has been running for a long time, but ad 2 is a completely new one. With the attention mechanism, ad 1 will focus more on features that could reflect historical informations, such as average click-through rate over the last 60 days. However, Ad 2 will focus more on the content features, such as what this ad is selling or what the average price of the offered products is. The last cold start case is system cold start. So when a new recommendation system is built, there is completely no previous knowledge on how this system performs. In this case, how do we provide reasonable recommendation results? Transfer learning is a commonly used technique for the system cold start issue. For example, we already have a recommendation model for ads engagement, such as click, comment, or share. Now we need a new recommendation model B that is for purchase. Since B is a completely new system, there's no previous data for it, but it can reuse model architectures, features, and even parameters from model A. So even without any previous data, B could still provide something reasonable. And as time goes by, Model B will keep accumulating and evolving based on the data from purchases. And this is all the content I have today. Thanks for joining the event. If you have more questions, please email or message me. I'm more than happy to answer them. And that's all for today. Thanks for joining and hope everyone enjoy the rest of the day. Thanks.